the first and most obvious important thing about the month of June is that it is when we move into summer, the time of the summer solstice. For those of you who don't know, the relative to its path around the sun, the axis of our planet's rotation is tilted 23 degrees. That sort of makes all the difference on the planet. So that, and it's tilted in a way where it stays tilted in that direction as it goes around the sun. So 6 months from, in December, it's tilted, the northern hemisphere is tilted away. Right? So what that means is this is the day in which light is shining directly on a point above the equator and where summer begins, right? The reason why summer, we'll get back to this, the reason why summer is hotter than winter is because sunlight is shining directly and in greater volume on the northern hemisphere. At the same time, of course, it's colder down here. So you don't want this to be the time you plan your trip to Antarctica, for instance. Depending on what your temperature situation is. So, and you can see that here. This diagram shows where the sun is shining most directly at the spring and fall equinox, when day and night are of equal length. It's shining right on the equator, which runs through Ecuador, right? And on the summer solstice, it's shining along this line here. This is the Tropic of Cancer, and then the fall solstice down here, winter solstice, I'm sorry, through the Tropic of Capricorn. So when you go out at noon, on June 20th or June 21st, depending on when it lines up, if you're standing in the right spot, looks like you're sort of in the Bahamas there, which is always the right spot, really, think about it. But if you're standing in the right spot, you will see the sun shining from directly overhead, which you will never see here. And similarly, same thing happens. So that's how, by the way, we first measured the circumference of the first person that we know of to do it correctly measured the circumference of the Earth in about 250 BC. A man in a Greek man in the Greek part of Egypt named Eratosthenes knew that there was a place a few hundred miles to the south where the sun shone directly into a well at noon. He put a stick in the ground, calculated the length of the shadow, and therefore the angle, and measured it against no shadow here, was able to estimate to within, we're not quite sure because of the unit of distance he used, but to within 85 or 95% of the correct value. So for people who think that for instance, Columbus discovered that the Earth was round, those people have known for a long time, and some people will know. Let's see. That's this. I want to show you this video. I added this to Patty's slide. I've seen it. Has anybody ever seen this video? Any remembers? It's quite old at this point. It's about students at Harvard graduation, being asked why it's warmer in the summer than the winter. And I just want you to listen to it. It's kind of interesting. It's a little bit loud, but in order to make it go over the computer to our members at home, so I apologize in advance. It starts with tolling bells. The bells are really loud.
Despite a lifetime of the very best education, the students in our classrooms are failing to learn science. Many of these students will graduate from college with the same scientific misconceptions that they had on entering grade school. To test how a lifetime of education affects our understanding of science, we asked these recent graduates some simple questions in astronomy. Consider, for example, that the cause for the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the
the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun. And it gets hotter when we get closer to the sun, and it gets colder when we get further away from the sun.
These graduates, like many of us,
So I'm sure that they, edited out all the people that answered it correctly. And of course, you have to make allowances for these people because they're Harvard students. Right? So, but it's kind of disturbing. The fact of the matter is, the orbit of the Earth is elliptical. It's not circular, but it's very close to being circular. The difference in distance between when the Earth is closest to the sun, furthest from the sun, is not nearly enough to make any appreciable difference in the temperature. And of course, well, two things. One is that it is closest to the sun, like in January. That blows that theory up. But also, you ought to be thinking, well, now why is it cold in Australia? But anyway, so it's just this is why we need to talk about the solstice when it happens. Of course, astronomers aren't necessarily all that fond of summer because although there are many great things in the sky in summer, it's also when night is shortest. So we have a harder time with viewing. For instance, if you get here at 7 o'clock in the winter, we can start showing you stuff. You get here at 7 o'clock now, maybe a bird, so which is fine with me. But all right, so
with Sagittarius and Scorpions.
yes, some of the best places. We'll talk about that a little bit. Some of the best places for viewing. Bear this in mind because it comes to. We'll get to this in a second. When you are the sky changes every day, right? If you think of me as being the Earth, like this as being the sun, in summer at night, when you're facing away from the sun, you're looking at all the stars in this direction, right? In winter, when you're facing away from the sun, you're looking at the stars in this direction. So as the Earth goes around the sun, you're seeing a different, view every day. And of course, every day, even every night, as we watch, the stars are moving as the Earth is turning, but we're also moving a tiny bit along that circular path, which we'll get back to in a minute. So these are some of the birthdays that are important in June. Giovanni Cassini was a very important astronomer. If you like Saturn, you know that there's a gap in the middle of the rings there called the Cassini gap. He's the one who discovered it way back in the 1600s, when telescopes were still kind of in their infancy. June is also the time that Charles Messier was born. He's also a very important astronomer. If you know any of the sort of important extrasolar system objects that we look at, like the Andromeda Galaxy here, several of them have names that begin with M, like this is M31. And in fact, it has two small satellite galaxies that are M32 and M110. We're going backwards. And Messier was a man whose passion was comets. And he hunted comets. And the way to look for comets is to search the sky with your telescope and look for little fuzzy objects that over the course of a few days move. So he found a whole bunch of fuzzy objects and was bitterly disappointed when they didn't move. So he basically made this catalog up as a way of saying to comet hunters, don't look here. Let me save you the trouble. Meanwhile, he was looking at star clusters and galaxies and nebulas and never thinking about how significant they were. Valentina Tereshkova was the first woman in space. And of course, Sally Ride went up in one of the early shuttle missions. She was the first American astronaut, American woman astronaut in space. So they both have their birthdays now in this month. This is not the year Sally Ride was born, this year she went up with the stick. The shovel was still pretty new at that point. Unfortunately, she's no longer with us now. Okay, so getting back to the whole thing about the sky changing every night, June has a few things to focus on in this lecture. This shows when sunrise and sunset are ish, of course, because it changes from day to day. Most of the planets that we would like to look at are up in the early morning. So this isn't a great time for planets, but that's not every June. That's this June. Talk about that a little further. We'll see the last of Mars for a while as it goes behind the sun. We have a full moon. We'll talk about that in a minute. And then there are several deep sky objects of tremendous beauty that are located in the summer sky. The summer sky is when we are pointed more or less at the center of the galaxy. So we're looking into like a really dense cluster of incredible objects. So there's lots to see in the summer sky. Okay. Okay, so the full moon is, I've never understood why, but these full moons all have names given to them by tradition. This is the strawberry moon. I guess it must have something to do with actual agriculture. This is when you I would assume when you plant and not when you harvest them. It's a bit early. It's the lowest moon of the year, but that may also have something to do with why it's called the strawberry moon, because when it's low in the atmosphere, things look redder. It's shining through more of the atmosphere to get to you, shining through more pollution, and a lot of it tends to make things look redder. That's because the ecliptic, I think there's a slide that deals with that. Hold on one second. Yes. So the ecliptic, the word ecliptic refers to the plane of the solar system. So the Earth is traveling around the sun in the ecliptic, and all of the planets, pretty much except Pluto, and there, I'm calling it a planet, all of the planets are traveling in that plane of the ecliptic. So what that means from our standpoint is when we're tilted towards the sun, the ecliptic looks like it's further north, when we're pointing away from the sun, it looks like it's further south. So in the summer, when we're pointed towards the sun, the axis of rotation, the ecliptic is quite low. So if you see planets or the sun or the moon, they're not the sun. If you see planets or the moon, they're going to be lower in the sky, which is why the full moon is going to be reddish looking. And in the winter, they tend to be high. So we have tilted in that direction. Was there anything else in that slide I wanted to catch up on? Hold on a moment. No, I think that covers it. The Old Farmer's Almanac. So as far as the planets are concerned, remember that as the Earth goes around the sun, the stars change basically in the same pattern every year. At such and such a day, at such and such a time, you'll be looking directly at this star every year. But that's not the case with the planets, because the planets are all going around the sun at their own speed. So Jupiter, for instance, takes 12 years to go around the sun, which means that it basically goes through one zodiac constellation, more or less, every year. And in case any of you wondered why, for instance, the Chinese zodiac or the Chinese astrology is based on a 12-year cycle, it's because they are based on where Jupiter is located. I'm not sure why, but at any rate, so the planets are moving at their own speed. So sometimes it seems like they're all out at a certain time of year, and sometimes it seems like they're not out at the same time of year. Right now, we're moving into a kind of fallow period for the planets in the evening, not in the morning. There's Mars. Mars is out in the morning, but it's getting closer and it's sinking closer and closer to the horizon. Saturn is out in the morning, and that is getting higher and higher each day. So if you get up 4 minutes before, 4 minutes later the next day, you should see Saturn in about 4 minutes earlier, I should say. You should see Saturn in the same place. So by the end of the summer, Saturn will be out at prime time, which is always our biggest sight. And Uranus is also out in the morning. For evening planets, the two big stars right now are Jupiter. Star was probably a bad choice of words. But Jupiter is leaving us fast. It's sinking further and further in the west every night, and soon it'll be behind the sun, and then it'll be out in the morning too. Right now, Jupiter is visible right around sunset, close to the trees there, and sinking. Jupiter is, this is an image by one of our members, Cliff Ashcraft. You can see, by the way, that the telescopes have a tendency to turn the image upside down. So that's why south is up. This painting, the great red spot is photographed. The great red spot is actually on the bottom cloud belt, top one. Jupiter, the other main feature that even through strong binoculars is good to see is that are the Galilean moons of Jupiter. So Jupiter has something like 95 moons. When I was growing up, the book I had said there were 12, but they've discovered a few more. Not as bad as Saturn, which I think went from 9 to 274. But Jupiter has 95 moons, but 4 of them are much larger and brighter than any of the other ones. And they are the moons that Galileo saw when he looked at Jupiter through his telescope. That's one of the clues he had to the fact that things were going around something other than the sun. So those moons are referred to as the Galilean moons of Jupiter. They are in order outwards: Io or Io, and Europa, Ganymede, and Callisto. Ganymede and Callisto are quite large. Ganymede is the largest moon in the solar system. It's larger than Mercury, so it's a planet-sized moon. Could go with an almost star-sized planet, basically. Jupiter is, of course, enormous. They can be seen through, if you can hold your hands real steady, through a strong pair of binoculars. And you might not see all 4 because it might be that one of them is right in front of the planet or right behind it as they go around. But that's what Galileo looked at them at several nights in a row and could find online the pictures that he drew showing how the moons were moving around, and he figured they must be in orbit. So that is also something to look at. And every once in a while, if you've got a good telescope, like our instruments here, one of the inner moons especially, Io and Europa, will pass between Jupiter and the sun, and you'll be able to see the shadow transiting the surface of Jupiter, which is kind of a cool sight. The moons move quite quickly. Well, the inner moons, Io, which is the innermost one, it looks like it's further away than Europa, but that's because Europa is back. This goes around Jupiter every day and a half. So an Io month on Jupiter is a day and a half long. It's supposed to be 28 days long. Even though the distance is fairly similar to that of our moon, I think. That's because Jupiter has tremendously strong gravity. It's just big. Whipped around and heated up, right? Io is so churned up by the tidal energy of Jupiter that it's basically melted on the inside. It's constantly erupting in volcanoes. They were the first volcanoes discovered anywhere other than on Earth in the solar system by the Voyager mission in the 1970s. I guess by the time it got to Jupiter, it might have been the 1980s, maybe, but it was launched in 1977. Europa, in the meantime, is further away. It's not quite as heated up, but it's basically a ball of ice with an ocean. The water water is tidally kept liquid. And it is a place where people think there could conceivably be life. There's a NASA mission called the Europa Clipper that's on its way there. Will unfortunately not get there for about 4 years, I think, but it's on its way. And actually, many of the, I think Ganymede and Callisto also both are thought to have subsurface oceans. So, sorry, I'm gonna go here. The other planet that's easy to spot is Venus. Now, Venus isn't such an exciting sight in the telescope because it's covered with clouds. It's very bright, so it tends to just be like a blurry, bright spot on the scope. However, it is cool to think you're looking at another planet. And the other thing that Venus shows that Galileo discovered, and also Mercury. Mercury is out, but it's almost always like already in the trees by the time it gets dark enough to see it. Is that Venus shows phases like the moon. And the reason is because Venus is closer to the sun than the moon. So when you're looking at Venus, you're going to see, unless it's all the way behind the sun, when it's full, you're going to see only part of it lit up. The other part will be dark, right? It'll be in the shadows. So Venus shows phases just like the moon, and that was another thing that Galileo used to deduce that they were going around the sun, not around the Earth. Venus and Mercury. And let's see. So Venus and Jupiter are sort of going towards each other right now, not literally. They're going towards each other to our apparent view in the sky. And in just a couple of days, that's a Tuesday, I believe, June 9th, they will be having a conjunction, which means they'll be quite close. I don't know what the limit to what makes a conjunction is, but so that you'll be able to easily see them both in the same field of view in binoculars and possibly even a telescope. And then Venus and the moon will be having a conjunction a little bit later, about a week later. Venus is very bright. What this says, the moon will be at mag, which means magnitude, at a magnitude of minus 10.3. So the magnitude scale is logarithmic, and it gets brighter as the number gets lower. So something that's magnitude 2 is much dimmer than something that's magnitude 1. The brightest stars are about magnitude minus 1, 1.5, I think. Correct me on that if I'm wrong, I'm serious. But so the moon is very bright. If you've ever tried to look at the moon through a telescope without a filter on it, low magnification, you know what it's like. It's not going to hurt your eyes. It's not like looking at the sun, but it's blinding bright. And Venus is, after the sun and the moon, is the brightest object in the sky. You can look at this. So the magnitude of Jupiter is minus 2.7. That's the next brightest thing, and Venus at minus 4.3. The full moon is at minus 12.5. Sun is super bright, obviously, minus 27. Don't look at it. So as far as stars are concerned, this is kind of a map of the June sky. You can see, I'm going to have to use the cursor for this, but this is the zodiac running through here. So we have Leo and Virgo, Libra, Scorpius, and Sagittarius, and then Capricorn over here, just one corner of it showing. So this is where the planets would show, if there were at this moment any of them to see. This talk is focusing mainly on these three constellations, Lyra, Hercules, and Scorpius, And I threw in an extra slide about this tiny little constellation here called Corona Borealis. We'll talk about that when we get to it. This is where some of the most basic sort of favorite deep sky sites of the summer are found. So these aren't necessarily, there are some bright stars here. This star Vega in the constellation Lyra is like the third or fourth brightest star in the sky. Antares is a very bright star because it's always low on the horizon, and because it's a little bit red to begin with, it always looks very red. But Hercules is a little faint and hard to see, but it's worth finding. The easiest part of Hercules to see is to find these two bright stars, Vega, and this is Arcturus. And then about 2/3 of the way across from Arcturus to Vega, there is this sort of weird shape called the keystone. That's the center of the constellation Hercules. Here's Hercules. I'm not sure why, but Hercules is upside down. I guess the ancient Greek astronomers were all lying on the ground looking up and weren't distinguishing up from down. So this is what the constellation looks like, except as you can see, north is that way. So Vega is the bright star very close by right here. And you'll notice that there's something here written that says Great Cluster. And here's that other constellation I mentioned, Corona Borealis, which means the Northern Crown. So Hercules has this object in it. Here's a closer up, a picture of Hercules. And this object called M13, so Messier labeled it, but he didn't discover it. It was discovered by Edmund Halley, who you know because of his comet that's named after him. Of course, Halley's comet occurred, many times before Halley, and the earliest record that I know of that we have of it is actually from 1066. There is, I think it's at the cloisters, there is a tapestry called the Bayeux Tapestry that shows the Battle of Hastings, and that was fought while the comet was in the sky. And so the comet is there with a inscription in Latin that says something like a star of ill omen. But at any rate, but Halley was the astronomer who discovered the periodicity of it, that every 76 years roughly it returns. But M13 was not a comet, therefore Messier wasn't interested in it, and Halley didn't have the high enough quality optics to see what an amazing object it is. If we look at it, M13, and this is a picture taken by Wayne Zuhl, who's one of our members. M13 is what's called a globular cluster, and it's the northern hemisphere's best globular cluster. So globular clusters are big balls of stars, basically. They are up to 500,000 or so stars. I think there's one in the southern hemisphere that may not actually be a globular cluster that has more stars, called Omega Centauri. And they're all gravitationally bound. Most star clusters are not, so that over time they will eventually fly apart. But these are gravitationally bound. They're thought to be remnants of smaller galaxies that were devoured by the Milky Way. All that remains is the core. They're comprised mainly of very old stars. But they are spectacular just to look at. If you can imagine, well, there is a famous science fiction story that's set globular cluster called Nightfall by Isaac Asimov. But there are 500,000 stars. They are crowded to much more closely than stars generally are. The nearest star to the sun is 4.2 light years away. These are probably like a light year or less, and they're or even half a light year, and they're gravitationally bound, which means they're constantly orbiting in an extremely chaotic way around their common center of gravity. And There are about 200 of them in our galaxy or around our galaxy. And they are mostly in the summer sky. There's a couple in the spring and a couple in the fall, and I know of two in the winter, I think, but one of them may not be part of our galaxy. And the reason why they're mostly in the summer sky is because they are surrounding the center of the galaxy in a halo, spherical halo. And so we're about a third of the way out in the galaxy, so we see them mostly in the summer sky when we're looking in that direction. It's one of the ways astronomers first figured out the size of our galaxy and what our location in it was by looking at sort of standard candle markers in all of these globular clusters, and they used that to sort of triangulate where the center of the galaxy must be. So M13, there's several in the summer sky, but M13 is the most beautiful one. It's not hard to find in Hercules. I can see it through binoculars, but through binoculars, it's not a super impressive sight. It's just cool to know you're looking at it. It's a little fuzzy spot. If we go back for a second, well, that's not a good diagram of it. You can see that it's in the keystone right along the lines, and there's actually like an asterism of 3 stars right around it. Make it easier to see. However, it blinds people to the fact that there's another really good globular cluster in Hercules that most people don't spend time looking for, that they might be better off if they did. It's over here called M92. Here's a picture of it. This is from Hubble. It's not from one of our members. It does point out one thing about globular clusters that's kind of interesting. You'll notice that some of the stars in this globular cluster are kind of blue. And astronomers didn't expect to find blue stars in a globular cluster. Blue stars are very hot stars and usually young stars. And these are supposed to be very old. And one of the theories about that is that with all the chaos in these globular clusters, sometimes meet our squeaky dome. Sometimes with all those stars packed so closely together and orbiting chaotically, sometimes they collide. And when they collide, they create a new, more massive star that burns hotter. So you have they're called blue stragglers. I think that this picture is kind of a nice expose of that. So we have these 2 beautiful globular clusters in Hercules. The next constellation is Lyra. Lyra means a lyre, not like a politician, but like a musical instrument, a harp. And it's supposed to be the lyre of Orpheus. It's known mostly, the one stars, these 3 stars, Alpha, Beta, Gamma, stars in the constellation are named after their order of brightness. So they are the 3 that are most easy to see. This one, Alpha Lyra, is called Vega. Vega is, as I mentioned, one of the brightest stars in the sky, and because these are Kathy's slides, I know what's coming next. Oh no, it's not yet. Probably one more slide further down. It's a small constellation, but it's filled with cool stuff. The Milky Way runs almost right through it. It sort of runs right over here. So when you look up at it through binoculars or a small telescope, you just see the sky packed with stars. The 2 most famous objects in it, there is another nice globular cluster in this that's not shown here, but M57, which we'll talk about, that's the famous ring nebula. We'll get to that. And then this star, Epsilon Lyrae, which is the 5th brightest star in the constellation. You can just about see it with the naked eye. It's also a very special star, and we will talk about that. It is supposed to have been, even though it's a harp, be born in the sky by an eagle. I'm not sure why. There's another constellation near it that is an eagle, so seems redundant. But probably something about the Orpheus myth that I don't know about. Even though by profession I'm a musician, and Orpheus is very important in the history of music as a subject matter. So Vega itself is a really interesting star. It's a very young, very hot, very bright star. It's quite a bit larger. Here's a comparison of Vega with the Sun. So some stars are much, much, much bigger than Vega, but it's quite a lot larger than the Sun. The cool thing about it is that it's orbiting very, very quickly. And it's orbiting so quickly so that you can see. I looked up the circumference of Vega, and it is about 8.5 million miles. Meanwhile, the rotation period is 12 hours. So, of course, you can't stand on a star unless you're wearing asbestos shoes, but which wouldn't do the trick. But that means you are going 8 million miles in 12 hours. That's how fast the star is rotating. And the effect of that is that Vega isn't spherical. Right? I mean, that's true of many stars and planets, but it flattens itself out, so it's like a fan. And you can see that in this picture. And Vega is a very bright star. Again, it's one of the brightest in the sky, largely because, I mean, it is intrinsically bright, but it's also very near us. It's about 26 light years away, I think. That's not really very near if you're a person and you're thinking of driving, because a light year is roughly 6 trillion miles. So, but it's by star standards pretty close. The next really cool thing in Vega is this star Epsilon Lyrae. If you can see it with the naked eye, it's a star. It doesn't look very prepossessing, but if you put your binoculars on it or a small telescope, you'll see that it's actually a double star. So many of the stars that we see in the night sky are actually binary or are multiple stars. Something's maybe it's 6 or 7 that I know of. And that means they are gravitationally bound. So these two stars are orbiting each other. But wait, there's more. If you then look through a more powerful telescope, you will see that each of those two stars is itself a double star. There's one here, and one here and one here. And you can see this through a scope, even when seeing is bad and you can't clearly separate them, that they're oriented sort of perpendicular to each other at the moment, right? So these stars are gravitationally bound to each other, orbiting around each other, but then the two pairs are orbiting around their common center of gravity. So that's a cool thing to be able to see. And then lastly, among the really famous objects, so there's Vega. Vega was, I knew this slide was coming. How could it not be? Vega was the star in the movie Contact that the character played by Jodie Foster first got signals from. It turned out the signals were only being routed through Vega, but nevertheless, she was hearing the signals from Vega. I think this slide is going to actually turn up in next week's presentation too. The other cool thing about Vega, though, is that Earth's tilted axis of rotation isn't steady in one. Over a long stretch of time, it spins like a top. The top is starting to topple to one side, but it continues to spin. And the result of that is that the North Pole points at different places around a 26,000-year cycle. We should be thankful right now that there is a North Star, right? Polaris is very close to the North Pole. They don't have one in the Southern Hemisphere. But in 13,000 years, Vega will be the North Star as the precession of the Earth's axis of rotation spins around. And then gradually, if you have patience to wait, we'll come back to Polaris. Right? But that's another cool thing about Vega. And then, so there's your 20, from 12,000 BC to 13,000, almost 14,000. That's about 26,000 years, excuse me. So the other incredibly cool object in Lyra is the Ring Nebula, which you can see. You can see it through a small telescope, but you can get a nice impressive view through our 24-inch when the sky is clear. It's called M57, and it looks like this. This is a picture by a wonderful former member of his club, passed away 10, 15 years ago, I'm not sure, Hank Adams. But this is his picture of the Ring Nebula, and this is a NASA picture. It looks like a smoke ring sky. It's quite cool, even when it's faint. By the way, I am thinking there's a little smudge. These lines were put in by Hank to point at this little smudge here, and I'm wondering if he was thinking he had a comment. I don't know for sure, but at any rate, so the Ring Nebula is a special kind of object. There's the word nebula is just the Greek word for cloud. So in some senses, when you live in New Jersey, there's a big nebula every day. but there are different kinds of nebula in space. There are nebula that are star-forming regions, that are big clouds of gas where stars are being born, basically. The Orion Nebula, which is one of the main winter sites, is one of them. But the Ring Nebula is, there's a nice Hubble picture of it. The Ring Nebula is the other end of the life cycle of a star. It's when the star reaches the end of its life. A star that's sort of an average sized star, like the sun, reaches the end of its life and it sloughs off the outer layers of its gases, and they expand outwards. Gradually, they will diffuse and disappear, and then if the star has strong magnetic fields, they'll get twisted into all sorts of cool shapes. The Ring Nebula isn't actually a ring. I think it's more like a tube that we are looking at edge on. But you can see the white dwarf that is the progenitor of the Ring Nebula is still shining in the middle there. So this is called a planetary nebula, because to astronomers in the old days, it looked kind of like it might be a planet to its ground, but it really has nothing to do with planets. It's the end of the life cycle of a typical star. So an average star like our sun, as it uses up its hydrogen, it swells up size, starts burning helium and some other things, and becomes a red giant. But then it casts off its outer layers in the planetary nebula. There are also many planetary nebulas in the sky. The Ring Nebula is just the most vivid one in the sphere. They look like different things. There's one called the Dumbbell Nebula because it looks like a dumbbell. There's the Owl Nebula, Eskimo Nebula. They all have different shapes caused by magnetic fields around their original objects. And then what's left of the star will become a white dwarf and gradually fade away. A larger star will swell up to a supergiant and then explode as a supernova, leaving either a neutron star or a black hole. There are actually a couple of black holes in the summer sky, but for obvious reasons, we can't really see them. But there's one in the constellation Cygnus, which is right next to Lyra. So that's what it says here. Now, this statement here, a nova, on the other hand, is the temporary brightening of a white dwarf before it fades again. That is needs a little bit more expansion. What happens for a nova is that is when you have a red giant and a white dwarf very close to each other, and the white dwarf, which is more massive despite it being smaller in size, is pulling off matter from the red giant and it's gradually accreting onto the star. And the problem is that that star can only reach a certain mass before the surface of it will explode in a giant thermonuclear explosion. That mass is about 1.44 times the mass of the sun. It's called the Chandrasekhar limit. And so novas happen when that happens, and the white dwarf survives, but there's a big explosion. By the way, sometimes the white dwarf doesn't survive and the whole thing blows up. That's another type of supernova called a type 1a supernova. But I bring this up about these kind of novas. They can go off again and again over a period of time. And there happens to be one in our part of the sky. So here's Hercules, which we talked about earlier. There's the M13, the gray Hercules cluster. There's M92. There's a small constellation called Corona Borealis. And, that little circle there is circling what looks like nothing other than a line through the map. There's a very faint star there that is a recurrent nova called T Corona Borealis. And the last 3 times it has gone off were all about 80 years apart, and we are now 80 years since the last time. So some of our members are diligently watching the skies to see what happens with T Corona Borealis. Unfortunately, it's late. But the problem is there's no actual reason to believe that periodicity is going to stay the same forever. So it might be 85 years this time, or whatever. So we don't know, but if it were to go off for a short amount of time, you would be able to see a star where you can't see one now. So if you look at this little crown shape, there's 1, 2, 3, 4, 5, 6, 7 stars in it. That's the brightest one. Next to the second star in, there would be another star that you could expect it. The T Corona Borealis having gone off. Don't hold your breath, but it could be soon. So the last constellation to look at tonight is Scorpius. Scorpius is one of the zodiac constellations. It is the scorpion, right? Supposedly, according to Greek myth, this is the scorpion that stung and killed Orion. And the gods put it up in the sky, but to keep Orion from getting upset, they put it up at the opposite end of the sky, so that Orion is out in winter and Scorpius is in summer. It's one of the few constellations that kind of looks like what it's called, like a scorpion, especially when you consider that these 2 stars in Libra used to be considered part of it and made up the pinchers. And then, of course, it curls around and the stinger is there at the end. So that's Scorpius. Scorpius has several interesting objects in it. One thing is that when you are, Wayne before was talking about Scorpius and Sagittarius, they are 2 stars that they're always low on the, 2 constellations, excuse me, they're always low on the horizon because they're really in the southern part of the sky, but because of that tilt, the Earth, you can see them in the summer. The center of the galaxy is right about in here. So when you're looking at Scorpius and Sagittarius, so for those of you at home, it's right about here. When you're looking at that, you're looking right in towards the center of the galaxy. Now, you can't see the center of the galaxy because there's a lot of gas and dust, but there is a strong source of X-ray emission there called Sagittarius star A, I think, which is star like asterisk, which is the black hole at the center of the galaxy. The brightest star in both of these constellations is the star Antares, which is in Scorpius. This is a red supergiant. So at some point in the future, it could be tomorrow, it could be 200,000 years from now or whatever, it's more likely to be that, I think. It will explode as a supernova. It's a gigantic star. The name Antares means, well, if you think about the Greek god Ares, god of war. He's the equivalent of Mars in Roman mythology. So Antares is the rival of Mars. Because it's also red. That's another. I always view this as being one line to here, and then the head is here, and those pinchers go out towards Libra. But Antares is so large that if you plunked it down where the sun is, we would be inside it, and so would Mars. You can see the orbit of Mars here, and this is Arcturus, which is the bright star that's straight up. That's a red giant, and that's our sun, right? So comparative size of those stars. So it's a very big star. Those red supergiants they're very unmassive. Yes, Marcus.
Your previous slide, Scorpius. Yes, so you should remember that Scorpius is in the Western Greco-Roman tradition. There are other traditions, cultural traditions, that view this, that have another name for this. The Hawaiians, the Pacific people, the ocean beings, they call that the fish hook.
Yes.
It certainly makes.
And you can see why.
Instead of a stinger, it's got a bar at the end, just like you would expect a good fish hook to have, right? There's also a really good, by the way, there's a really good globular cluster in Scorpius. There's more than one, I think, but there's one right here called M4. It's quite large, but it's hard to see because of the fact that it's low in the sky and there's light pollution. We can pick it up on the telescopes here, but in binoculars, you might not be able to see it, even though you can see similarly bright objects that were high up. Antares does have a companion star, but it's very difficult to see for obvious reasons. It's like looking for a cigarette lighter next to a 5-alarm fire. You're not going to have an easy time seeing it. So that's Antares B. That brings us basically to the end. Here's a little quote from Walt Whitman, who has a lot of good quotes about nature. This one is that every cubic inch of space is a miracle.